So in the last lecture, we have seen one of the method for computing the state feedback gain. So that method was known as the eigenvalue assignment. So we stressed onto one fact that if the system is controllable, then given a set of eigenvalues, we can place the eigenvalues of the closed loop system. Right? Now the another question arises that how do we get the information about the set of desired eigenvalues. So there are different ways of computing the set of desired eigenvalues. So you have studied in your possibly you have studied in your UG control course some methods from the root locus diagram or from the Bode plot by taking into account the transients and the steady state characteristics. So first of all, it depends on the performance criteria, that what performance criteria we are targeting, meaning to say what are our control objective. It could be the rise time, the overshoot, or the settling time if we speak these criterion in terms of the time domain. In terms of the frequency domain also, the responses not only depend on the poles, but it also depends on the zeros. So far we have focused onto the location of the poles and also placing the location of the poles by using a state feedback. But the overall response is also affected by the location of zeros. The factors which affects the selection of the poles, first of all, is the zeros. So in the last lecture we had seen that if by using the state feedback you are able to place, or you might happen to place the poles at those locations where the zeros of the plant are already there, then it may lead to the state of unobservability, which we will discuss in the coming weeks. So we need to take care that first of all, whatever the poles we want to place for the closed loop, it should not overlap with the zeros. Second point is the magnitude of U, which takes into account the saturation or burnout. So this point is more from a practical point of view. Say for example, if you have certain plant, then those plants are basically actuated by some actuators, and we take some measurements with the help of some sensors. Now, depending on some actuator limits, we need to put some constraints on the signal U. So it might happen that you have designed a controller in such a way that the control signal always leads to the saturation, or it leads to the maximum value to what the actuator is capable of. So we need to take care of that because this is not a very desired condition or scenario. The rise time, settling time, overshoot is pretty much obvious. The most importantly is the bandwidth of the closed loop, which takes into account the frequency domain characteristics, and there is a very strong correlation between the time domain characteristics and the frequency domain characteristics, which possibly you have uh, studied during your UG control course. So all in all, it involves some compromises among many conflicting objectives. So in the sense that when we started this week, we put two different objectives to synthesize the control law. Meaning to say, when we discuss about the open loop minimum energy control. So the first objective was of the controllability, and the second was of the, and there was a second objective also. Now there are two good references which I would like to highlight here. So the first one is by Stephen Boyle on linear controller design, limits of performance. So this is a book. So many chapters of this book discusses about it, what performance is, or what are the limits on the performance of the closed loop system you can achieve. The second is a paper by Carl Ostrom on limitations on control system performance, which was published in European Journal of Control in 2000. So this paper is also quite good, which discusses an overall overview of the performance of the control system. So we won't go into the details of computing the set of desired eigenvalues, but we will see some guidelines that how one can specify the set of desired eigenvalues. So just some guidelines. Say for example, on the left hand side, this one is basically the S plane in the continuous time domain, and this one is the Z plane in the discrete time domain. So the first of all, the first objective that all the eigenvalues of the closed loop system should be onto the left hand side. Now here we are specifying an additional control objective that all the eigenvalues should be inside this region C, which is defined by this region. So when you see this region in the S plane, by drawing the damping coefficient line, you can assess some of the parameters. Let's say the sigma, which is the real part of the S plane, the theta, the angle which it makes from this axis, and also the radius of this semicircle. So if you have larger the sigma, the response of the closed loop system would be faster. If your closed loop poles happens to be having the larger value of sigma. So this implication you could see pretty much straightforward. Say for example, if you say the larger the sigma, let's say in terms of the transfer function, let's say if we have a transfer function some s plus sigma. Okay, so s plus sigma, into the sense I can also write this as equivalent to 1 by sigma and 1 by sigma s plus 1, and replacing 1 by sigma by tau, so I can write this tau by tau s plus 1, where tau is the time constants. So if we have larger the sigma, the value of the time constant tau would be smaller, meaning to say the response would automatically be faster. But if we have larger the theta, larger the overshoot. If we have larger the r, the response of the system would be faster. With the faster response, as we had noted in some tutorial problems, when we, if you recall some of the problems we discussed during the controllability as a part of the tutorial on controllability. So if we want to reach to some desired state value in t1 amount of time, the lesser the time t1, the faster is the response and faster is the energy. So this is obvious that larger the r, faster the response would be, and u would also be larger in that particular case. At the same time, bandwidth will also be larger, and the resulting system will be more susceptible to noises. Okay? So this is in the S plane, equivalently is drawn in the Z plane. So most of the time in this week we would discuss the design of the controllers in the continuous time domain. All the results, whatever we discuss, would be directly applicable onto the discrete time systems as well. Right? So we will now discuss another method of computing the state feedback gain for the eigenvalue assignment problem. So in the last lecture, we studied one way of computing the state feedback gain using the controllability matrix. So this method has some restriction that the selected eigenvalues cannot contain any eigenvalues of the plant itself or of the A. Okay. So here first we will discuss the algorithm for computing the state feedback gain, and then we will try to justify that algorithm by computing certain conditions which are necessary and sufficient for this algorithm to work. So the data which we supply to this algorithm is the pair A comma B, which is supposed to be a controllable pair, where A is an n-dimensional matrix, and for the moment we are taking U as a scalar. So in that case we would be having n cross 1 dimension vector and a set of desired eigenvalues. So based on these three information, the result we want to compute 1 cross n real vector k such that the eigenvalues of this matrix, of the closed loop matrix A minus bk, has the set of desired eigenvalues that contain no eigenvalues of A. So the first step is we select an n cross a square matrix F of dimension n that has the set of desired eigenvalues. Now the form of f can be chosen arbitrarily, and we'll be discussing it after the justification, that what f matrix you can select. The second step is select an arbitrary 1 cross n vector k bar such that the pair f transpose and k bar transpose is controllable. Now if you recall in the last algorithm, based on the information of the coefficient of the characteristic polynomial of the A matrix and of the set of desired eigenvalues, we pre-specified this k bar. Now here we got some freedom that once we have a set of desired eigenvalues, first of all the form of f matrix could be anything such that it is having the those eigenvalues. Now here we can select any arbitrary k bar vector. The condition which we need to satisfy is that the pair f bar, f transpose and k bar transpose is controllable. Third, we solve for the unique matrix T in the Lyapunov equation given by At minus T times F is equal to Bk bar. The final step is, once we have obtained the T matrix, we compute the feedback gain vector k as k bar into T inverse. Okay. So once we have selected a k bar matrix such that this pair is controllable, then we can use the MATLAB Lyapunov function, this Lyap function, to solve this Lyapunov equation. So you could use this function in a similar way what we have discussed during the stability week. Okay. And once this k bar matrix or k bar vector is selected, we can solve this Lyapunov equation to solve for T, and after putting T here we would obtain the state feedback vector. So how do we make sure that once we that whatever the k we have computed would going to yield the set of desired eigenvalues? So here we will see the justification of all these 4 steps so that we can ensure that once we plug in this k state feedback vector, we would obtain the closed loop as this one, which would contain all the set of desired eigenvalues that contains no eigenvalues of A. So the first point is that if T is non-singular, if the matrix T is non-singular, then I can write k bar is equal to k into T from here, and the Lyapunov equation can be replaced, in which the k bar can be replaced by kt as. So for example, if I put k bar is equal to kt here and they take it on the left hand side, I would have A times T minus B k times T, and after taking the T matrix common, the rest of the thing is A minus Bk, and we take this part onto the right hand side, so it would give me Ta. Now again taking this T matrix onto the right hand side, I would have A minus Bk is equal to Tf T inverse. Now if you pay close attention to this equation, the same equation we have used when we discuss about the similarity transformation, where T could be any non-singular matrix, and here T happens to be a transformation matrix, meaning to say that, and we know that under the transformation the eigenvalues do not change. So whatever the eigenvalues we would specify in the matrix F, it would definitely be of the matrix A minus Bk. And this is what we expect the result of this algorithm. Now thus the eigenvalues of this matrix A minus Bk can be assigned arbitrarily except those of A as well. Now if A and F have no eigenvalues in common, that is the plant and the closed loop system have no eigenvalues in common, then a solution matrix T exists in this Lyapunov equation for any k bar and would be unique. So this is the most important point here, which we would formulate into a result, and we will see the proof of this equation as well. Because the most important thing in all these four steps, that t, because here we solve for the unique t, so where we should know first as a preliminary step that whether that t exists or not. Because f is the user defined or is computed based on the objectives. K bar is also user defined based on this condition, which can be satisfied. Now using this k bar and f, we solve for this t. So we need to ensure that whether that such t exists or not, first of all. On the other hand, if A and F matrix have common eigenvalues, a solution T may or may not exist depending on B k bar. So in order to remove this uncertainty, we require A and F to have no eigenvalues in common. So this particular point in the first statement, we have seen this while, if you recall the result on the Lyapunov stability for linear time invariant systems. So this was one of the point which we have highlighted. So what remains to be proved is the non-singularity of T. So at the same time, if T happens to be a non-singular, meaning to say that it would be unique. Okay. So this is one of the important result, that if these matrices A and F have no eigenvalues in common, then the unique solution T of this Lyapunov equation is non-singular if and only if the pair A comma B and F bar transpose and K bar transpose are controllable pairs. So we need the controllability of the pair A comma B and also of this one, which is an additional condition to solve for this Lyapunov equation. So we'll see a detailed proof of this result, so that by doing the proof, we want to recall many of the basic concepts, so that it would also help you to carry out your own proof of your own results. So we shall prove the theorem for n is equal to 4, but it would also be applicable for any n-dimensional system. So recall that the characteristic polynomial of the plant or of A matrix is given by this polynomial for n is equal to 4, where alpha 1 to alpha 4 coefficients are already known. Okay. We also know from Cayley-Hamilton theorem that if I replace S by the A matrix, this would also be equal to 0. Okay. So let's see the proof. So here we define a matrix which is delta of F given by this one. Now this is a matrix we can say, let's say F tilde, and we know delta of A would be equal to 0, but delta of F would never be equal to 0. Okay. So we define one matrix by replacing S by F in the characteristic polynomial. So if lambda I bar is an eigenvalue of this matrix F, then delta of lambda I bar is an eigenvalue of this matrix. So this you can take it as an exercise for a generic n-dimensional system, but we can see through one example that how this statement is true. Say for example, we take A as an identity matrix. If A is an identity matrix, then we know that the system is an unstable system. Okay. The next step is to compute the determinant of SIM minus A, which is delta of S, and it would be given by S minus 1 of square or S square minus 2S plus 1. just for the confirmation, we can verify that delta of A would definitely be equal to 0. So if I substitute S by A matrix, we would have S A square. So A square again would be identity minus 2, it would be twice into Y plus an identity. So it would definitely be 0. So now define another matrix. Let's say we want to place the eigenvalues of the closed loop matrix uh, to let's say -1 and -2. So I form another matrix. Let's call it F tilde, which is delta of F, and is given by the square of this matrix would be 1 0 0 4 minus, so I write plus and it would become 2 4 plus identity. Okay, so this matrix happens to be okay F tilde. Now it says if lambda I bar is an eigenvalue of F, so lambda I lambda bar are -1 and -2 of this matrix. So if we need to compute and verify that delta of lambda I bar is an eigenvalue of this matrix F tilde. So delta of, so once we compute for delta of -1, delta of -1 would be equal 4, and again delta of -2, delta of -2 would be 9. So it is clear now that delta of lambda bar I are 4 and 9, which happens to be the eigenvalue of this F tilde matrix. Okay, so here we have taken one example to verify this statement, but you can take it as an exercise to show in generic for an n-dimensional system that this statement would hold true. Okay, now taking this statement further, because A and F matrix have no eigenvalue in common, we would have delta of lambda I bar is not equal to 0 for all eigenvalues of F. Okay, then we compute the determinant of this matrix. We have, so we know that determinant of any matrix is the multiplication of all its eigenvalues. The eigenvalues of this delta F is delta I lambda, delta of I lambda, and the product of this delta of lambda bar I over all I would also not be equal to 0, because this is not equal to 0. So this delta F is a non-singular matrix. Let's go further. Then we substitute, taking from Lyapunov equation, AT is equal to TF plus BK bar into another matrix which we are defining by as A square T minus TF square. Okay, so this matrix we are defining, and we want to substitute the Lyapunov equation into this equation, which yields that A square T minus TF square is equal to, so here we would have I can take A matrix common, so the rest matrix would be AT, and replace TF plus BK bar minus TF square, and then clubbing this A TF matrix with this matrix and taking F matrix common, I would have AT minus TF and AB K bar the rest of the part, and this AT minus TF is nothing but BK bar. So I can write A square T minus TF square as equal to AB K bar plus BK bar F. Okay, the relevance of doing this procedure is would be clear in the next slide. So proceeding forward, we can obtain the following set of equation. So we start with I into T minus T into Y would definitely be equal to 0. Then AT minus TF, we know it is already a Lyapunov equation. Further, a square t minus tf square, this is what we have computed. Now going forward for power 3 and power 4, you can also simplify by yourself the right hand side to whether they are coming equal to this or not. Okay. Now we multiply the first equation by alpha 4. So we multiply by this alpha 4. Multiply this equation by alpha 3 both sides. This is by alpha 2. This is by alpha 1. And this remains as it is. Okay, or by 1 or by I. Okay, and we will sum them up. So you would notice that T matrix we can take it common, and the rest of the elements are, or in the bracket would be alpha 4 plus a times alpha 3 plus a square alpha 2, a cube alpha 1 and a 4. Okay, so we would obtain this delta of a into t minus t into delta of f would be equal to minus t into delta of f. Why? Because from the Cayley-Hamilton theorem, this part would reduces to 0, because delta of a is nothing but equal to 0. Okay. Now looking at the right hand side, I can rearrange the right hand side by this matrix in times this matrix times this matrix. It is just a simplified version of taking all this form by multiplying each and every equation by alpha i's. Okay. Now here, this is the most important thing. So delta f, we have already shown that it would be a non-singular matrix. This matrix being a upper triangular matrix, it would always be a non-singular matrix. This matrix would be non-singular if and only if a comma b pair is controllable, and this matrix is non-singular if and only if f transpose and k bar transpose is controllable. So in that case, all these matrices, this and this matrix are non-singular matrices. So T would definitely be a non-singular matrix, and this only happens if the matrix A and the matrix F have no common eigenvalues. Now if either of the matrix is uncontrollable, if this matrix or this matrix or either of the pair is uncontrollable, then your T matrix would be a singular matrix. So this establishes the if and only if condition. Okay. Now commenting on the selection of f, given a set of desired eigenvalues, there are infinitely many f that have the set of the eigenvalues. So we can take two forms. The first form could be if we form a polynomial which we had seen earlier from the set, we can use its coefficients to form a companion form matrix, so that all the coefficients I can arrange into this way, where all these coefficients are of the f matrix. If I write the characteristic polynomial of the f matrix, these would be the coefficients, and arranging all these coefficients into this form would yield me a companion form matrix whose eigenvalues would definitely be the eigenvalues of the required eigenvalues. Now this particular f matrix we have also seen in some of the tutorial problems. Let's say if there are some complex eigenvalues and we want to specify a real matrix, then we can write the complex eigenvalues as this block, and the complex eigenvalues should definitely occur in with its conjugate pair. Okay, so here it contains 5 eigenvalues and it is a block diagonal matrix. So one block is this one, and then another block is this one, and another block is this one. Okay, so 2 eigenvalues are here, 2 are here, and one is here. So there are different f matrix which you can form so that it could contain the required set of eigenvalues.